In this slide, we're going to take a look at Johannes Kepler's three laws of planetary motion, and they've been sketched out here as A, B, and C. Let's start with A. Johannes Kepler's first law of planetary motion said that planets trace elliptical paths around the sun. We've generalized this now to say that any object that is orbiting is always going to follow an elliptical path. So it could be a planet orbiting the sun. It could be the moon orbiting the Earth. It could be a satellite or space station orbiting the Earth. It could be the solar system orbiting the Milky Way galaxy. But whatever the case, anytime you have an orbit, those orbits are always elliptical. It turns out, if you dig into it, this results from the nature of Isaac Newton's law of gravity, right? But we're not going to get into that. So the first thing you have to understand about A is that this path is an ellipse. The second thing you have to understand is that part of the way an ellipse is defined is you could take two pins and put one right here and one right here. And those are called the focus points of the ellipse. And then if you have a piece of string that you've attached to these two pins, and you take a pen or a pencil and you trace out a line, that's always going to give you an ellipse, right? The second part then of Kepler's first law is that the sun is always at one of those focal points, or always at one focus of the ellipse. So, point one, planets always follow elliptical paths. Point two, the sun is always at one focus. Kepler's second law, illustrated here in B, says that planets have to trace out equal areas in equal amounts of time. In other words, this shaded section right here has an equal area to this shaded section right here. Each of them took 6 months. But you'll notice that right here, the planet did not go very far in 6 months. That means it has to be going more slowly. Over here, the planet went quite a longer distance in 6 months. That wasn't an English sentence. The planet went much further in 6 months, which means it has to be going much faster. Here's the takeaway. When the planet is furthest from the sun, it's moving the most slowly. As the planet moves closer and closer to the sun, it speeds up until at its closest approach, the planet goes as fast as it ever will. And then as it moves away from the sun, it slows down, slows down, slows down, speeds up, speeds up, speeds up, slows down, slows down, slows down. You've seen this all before. If you've ever stuck a coin into a wishing well, you've observed this happen where the coin speeds up as it approaches the center and the coin slows down as it gets further away. Here's the final one of Kepler's planetary laws. His third law has got some complicated stuff here, but the takeaway is this. The takeaway is that as you get closer to the sun, it takes you less time to orbit. In other words, Mercury goes around the sun the fastest. As you move away from the sun, planets take longer and longer and longer times to orbit the sun. So Mercury goes around the sun in 88 days. Venus is a little further away. It takes 225 days to orbit the sun. Earth is a little further away. It takes 365 days to orbit the sun, and so on. By the time you get out to Jupiter, it's taking 12 years to orbit the sun. Saturn takes 30 years to orbit the sun, and so forth. Again, you've observed this. When a penny goes into a wishing well, at first it goes very slowly, but as it spirals into the wishing well, it goes faster and faster and faster and faster until finally, plop, it goes into the center of the wishing well.